You may have thought that time travel was only something from the movies, a captivating science fiction dream, but ultimately impossible. But the truth is, one of the greatest minds in human history, Albert Einstein, once said, "Time does not flow as you think." In his equations, there are strange hints that time can stretch, slow down, and even bend. And if that's true, then perhaps time travel is not just a fantasy. Now, dim the lights, settle in, and relax, because what you're about to hear might make you look at your watch in a completely different way. If you love journeys that explore the boundary between science and the seemingly impossible, don't forget to hit subscribe and like this video so you can join me in the mysteries to come. Now then, let's begin decoding time. Our world is vast. Earth alone holds countless wonders, enough to fill an entire lifetime of discovery. But that also means that out there, beyond our planet, the universe is even more expansive and filled with more awe-inspiring possibilities. We know how humanity can expand its reach and become an advanced civilization. But at the same time, we also know that the end of that road is marked by the limits of the universe's expansion. The speed of light is the upper bound for all things, and yet space itself is expanding even faster than that. So, the idea of humankind truly traveling the stars no longer seems feasible, but is that really true? Together, we're going to explore how to overcome that very limit. If space is expanding faster than the speed of light, then we must find a way to manipulate space itself in order to cross the boundaries of the cosmos. And when we speak of bending space, we must also speak of the glue that holds the universe together: gravity. Gravity is a concept absolutely essential to the existence of all things. But the truth is, gravity is not really a force at all. And in just a moment, you'll understand why. Gravity is one of the four fundamental interactions in the universe alongside electromagnetism, and the strong and weak nuclear forces, each of them irreducible and foundational. Among these, gravity is considered the weakest interaction, yet it holds the greatest influence on the grand scale of the cosmos. Gravity is the adhesive that brings the universe together. It keeps planets orbiting stars, it makes them spin. It gives rise to tides on Earth, and at its most basic level, it's the reason you're being pushed against the surface of the Earth. Yes, you're not being pulled by Earth, you're being pushed. But why pushed? Isn't gravity described as the glue that pulls everything closer together? That's how we all thought it worked at first, even Newton did. But he had a far more profound understanding of this mysterious force. In 1684, mathematician and physicist Isaac Newton proposed an explanation for the motion of the planets. In it, Newton described gravity as a force, more specifically, as the attractive force between two objects with mass, based on the distance between them. Simply put, this means that any two objects with mass will attract each other. The strength of this attraction depends on how massive they are and how far apart they are. For example, a very heavy object will exert a stronger pull than a lighter one, but if that heavy object is far away, the force of attraction is significantly reduced. Like all scientific theories, Newton's explanation was accepted as truth because it could be applied to reality and produce accurate calculations, and indeed, Newton was right. His formula for calculating gravitational force worked across the board with almost no measurable error. It was so accurate that it even led to the discovery of Neptune in 1821. Newton's brilliance was undeniable, and his insights allowed scientists to calculate celestial mechanics with extraordinary precision for over 200 years. But if Newton was right and gravity is a force, then why are we here discussing it again? Well, Newton's formula was right, until it wasn't. This brings us to the second great mind in the story, Albert Einstein. Newton's gravitational formula works wonderfully within Earth's boundaries. But once we venture into the wider cosmos, calculating the interactions of stars and planets, small discrepancies begin to appear. For example, when astronomers studied Mercury's orbit, they noticed an unusual precession. While all planets follow elliptical orbits around the Sun, Mercury's orbit not only traces an ellipse, but the ellipse itself slowly rotates over centuries. Scientists argued about this for decades, but no existing explanation could fully account for the phenomenon. Then Einstein began to think. In 1905, he proposed a new theory of interaction in the universe. That theory would later be known as the theory of relativity. It can be understood as a model of how massive objects interact with each other across space. At the time, Einstein was still an unknown scientist, far from the global icon he would become. But, like Newton's formula, Einstein's theory was put to the test and slowly. More and more scientists came to agree. Einstein was right. In fact, the theory of relativity turned out to be even more accurate than Newtonian mechanics when applied to the universe at large. So, does that mean Einstein was right and Newton was wrong? Not exactly. You can think of Einstein's theory as an extension of Newton's, a more complete answer to the very question Newton had puzzled over his entire life. You see, even though Newton formulated the laws of gravity, he was never able to explain where this force came from. He could describe how gravity worked but not why it worked. His theory said that all objects with mass attract one another, but he couldn't say why they did. The answer lay in Einstein's theory. The simplest way to understand gravity according to Einstein is this. Gravity is the curvature of spacetime caused by the presence of mass. Remember those science demonstrations where a heavy ball is placed on a stretched fabric, creating a dip in the surface? That's essentially how Einstein explained gravity. It isn't a force in the traditional sense, it's the bending or warping of the spacetime fabric caused by massive objects. Okay, we can use this as a simplified analogy. It's not 100% accurate, but it provides a good foundation for further understanding. Because the concept of spacetime is both incredibly complex and beautifully simple, and Einstein used it as the foundation to explain gravity. So, to understand gravity, we must understand spacetime. And to understand spacetime, we need to dive into Einstein's mind and witness how he perceived the universe. Let's lay everything we think we know on the table. First, according to Newton's first law, all objects with mass tend to maintain their state of equilibrium. This means that an object at rest will want to stay at rest, and an object in motion will want to maintain its velocity. Nothing will move or change its speed unless acted upon by an external force. This is the foundation of inertia. The heavier the object, the more inertia it has, and the more force is needed to make it move. To Newton, no object could move on its own without an external force acting on it. But to Einstein, that's not necessarily true. When you lift an object, it gains potential energy, and when you let go of it, even without any direct force applied, it still falls. This falling is the object's way of returning to its state of balance. According to Newton's law, if the object never hits the ground, it would continue to fall at a constant speed. That still aligns with Newton. But in this case, the object falls because we dropped it. So then how do planets fall? Let's go back to the example of stretching out a sheet and placing heavy balls in the center. If we put a heavy ball in the middle, the lighter balls placed nearby will roll toward it. The lighter balls, which were previously at rest, suddenly start to move toward the heavier one without any obvious external force acting on them. So, it turns out that objects at rest can move without needing a traditional force. What about an object in motion trying to maintain its velocity? If you roll a ball across that stretched sheet, which now sags in the middle, it will move in a curved elliptical path around the dip. From this interaction between balls on a stretched sheet, we can immediately grasp the core principle behind the movement of planets and stars in the universe. Nothing is actually being pulled, and nothing is pulling anything else. Everything is simply falling toward a more massive object. Newton wasn't wrong, it's just that his formula didn't account for the curved fabric of space. Einstein was the one who imagined that sheet, and with that, everything was explained much more clearly. But are we really going to stop here, conclude that Einstein merely refined Newton and gave us a better explanation of gravity? No. We're here to explore and understand spacetime itself. So what does all of this about gravity have to do with spacetime? The truth is everything is connected, as we discussed earlier. Anything with mass affects the space around it, creating an effect we call gravity. That means in areas of space filled with massive objects like stars and planets, the space around them is constantly being curved and distorted. But it's not just space. Time itself bends and warps just the same. Until now, we've had a fairly rigid view of time. That 15 minutes is always 15 minutes. That we measure work and rest in units of time. That time has a past, a present, and a future. But with Einstein's theory of relativity, time can stretch or shrink. But why is that? To understand this, we need to consider three foundational perspectives from Newton, Einstein, and James Clerk Maxwell. Maxwell established that the speed of light is a constant. No matter where you are or what perspective you observe from, the speed of light remains the same. Now imagine this scenario. You're standing next to a railroad track. A train is passing in front of you. Suddenly, two lightning bolts strike at the same time, one in front of the train, and one behind. Interestingly, you are standing exactly between both strikes. From your position, you see both flashes of lightning simultaneously, right? But what if you were on the train as it moved past the two lightning strikes? What would happen then? Even though the lightning bolts strike at the same time, because you're moving toward one and away from the other, you'll perceive the closer strike first and the second one slightly later. Yet the speed of light still remains constant c. So why does one bolt appear to happen before the other? Let's compare the two experiences from two different perspectives. From the outside, you see the two lightning bolts strike at the same time. But from the train, you perceive them as happening at different moments. How is it possible that the same event can yield to different results and both be correct? The speed of light is constant. The distance remains unchanged. That leaves only one variable that can shift, and that's time. This leads to the conclusion: time can stretch or compress, depending on the speed at which an object is moving through space. With this line of reasoning, Einstein realized that speed means nothing without time. Yet, we still don't have a concrete definition of what time actually is. Could it be that time flows identically everywhere in the universe? Is 1 hour on Earth really the same as 1 hour on a planet billions of light-years away? Einstein concluded that time at any point in the universe is tied to its location. In other words, time and space are not separate, they are one. And we call this unity spacetime. Everything moves through spacetime. Space and time don't function independently. In fact, they are a single fabric. Space-time bends and curves under the influence of massive objects, and this curvature is what we perceive as gravity. For example, Earth, being less massive, falls toward a more massive object, the Sun, so any object moving near something with large mass appears to be drawn toward it. But it's not actually being pulled. Instead, its straight-line motion is being curved by the immense mass. The best analogy is still the stretched sheet with a heavy ball in the center, which we've mentioned before. In the universe, no direct force needs to act on the planets, yet they continue to move, seemingly on their own. Moreover, this curvature of spacetime creates the orbits of stars and planets that we observe. But from here, we can pose a fascinating question. If space and time are one, and we can move forward and backward in space, then, could we do the same in time? Before diving into the fourth dimension, we need to revisit the idea of 3 dimensions. What exactly is a dimension? More specifically, what is a spatial dimension? Let's return to the basics. What is one dimension? Simply put, you can imagine it as a straight line between 2 points A and B. If we lived in a one-dimensional world, our entire lives would be spent going from A to B and back again. No change, that's all there would be. So what about two dimensions? That's when you add a new point C outside of A and B now. Instead of just moving back and forth, you can also move sideways to and from point C. Think of spatial dimensions as directions of movement. One dimension is movement along a single line, say, up and down from A to B. Two dimensions introduce a sideways option from A to C or B to C, and so on. Then, the third dimension adds yet another point D outside of A, B, and C. This allows you to move up and down. If we take point A as the origin, and consider B, C, and D as different directions, we now have what's familiar in high school math, a coordinate system with axes labeled 0, x, y, and z. But where does 4D fit into all of this? We're 3D beings living in a 3D world, so imagining a fourth spatial dimension is extremely difficult. Why is it so hard? Here's an example. Imagine you live in a 2D world. You're about to experience what a 3D object looks like from that perspective. In 2D, you only see forward, backward, left, and right. Now, suppose a 3D object like my hand passes through the 2D world. What would the 2D observer see? First, they'd see a dot. Then two dots, then four dots. The dots grow larger. And then another dot appears next to them. Eventually, all the dots merge into a single big shape. Now, you tell the 2D observer, all those dots were the same object. Do you think they believe you? So, can you imagine a 4D object in a 3D world? Probably not. But thankfully, even though we can't create a 3D object in a 2D world, we can represent it using a coordinate system with three vectors, 0, x, y, and z. So, can we represent a 4D object using a 3D coordinate system? The answer lies in Minkowski space. Hermann Minkowski was a brilliant German mathematician known for solving algebra problems through geometry. But what he's best remembered for is developing the ideas of his student, that student, none other than Einstein. With his visual approach to mathematics, Minkowski reimagined Einstein's spacetime concept using geometric diagrams. From this, we gained a clearer, more intuitive way to understand the four-dimensional space Einstein envisioned. To grasp the model we're about to explore, you'll need to recall everything we've discussed so far and let go of all familiar ideas about space and time. Why? Because this is an extremely abstract concept. Are you ready? First, just as we represent the three-dimensional world using three vectors on a two-dimensional plane, we can also represent our three-dimensional world as a plane in the following model. The horizontal axis here represents space, and every point in this space has a specific coordinate. Next, we introduce the vertical axis. This represents time. Because space is measured in units like kilometers, meters, or centimeters, time should also have a corresponding unit. Here, we can use the speed of light as the baseline since it's the universal constant. Distance equals speed times time d equals c times t. So, time can be represented using this relationship. An object that doesn't move through space still progresses through time. Therefore, in this model, an object at rest will always move upward along the time axis. That upward line is the object's world line. Keep that term in mind. From here, we can see that the movement of an object through spacetime can be represented as follows. For example, if an object moves from point A to point B at a speed of 10 km per hour, and the distance between A and B is 2 kilometers, then its vector of motion in the model will have a slope corresponding to its velocity. Following this same logic, a light particle moving through spacetime would be represented as moving at a 45-degree angle. Since time is measured based on distance divided by the speed of light, the light particle moves through both time and space at the same rate when traveling at light speed. From this, we also know that an object's world line and space coordinates will change depending on its velocity. Only the speed of light remains constant. Now let's begin the experiment. Suppose a beam of light is emitted from a certain point in the universe. Let's call this event A. Since light spreads in all directions, it would normally be represented as a circle. But because a light particle also moves through time, what we actually see in the model is a cone shape. This is the spacetime model Minkowski developed based on Einstein's theory of relativity. However, up until now, we've only described Minkowski's model. So how does it connect to relativity and why is it said to be an extension of it? Let's go back to the example of the lightning strikes and the moving train from the previous video. Thanks to that example, many of you asked questions about the relativity of space and time, and why that situation demonstrates time dilation. Perhaps after this next example, things will become even clearer. When we add those two lightning strikes to Minkowski's model, we now have two light sources representing the two bolts of lightning. And with two sources of light, there will be two light cones in the spacetime diagram. In the train example, our first observer was standing exactly between the two lightning bolts, so they saw both strikes happen simultaneously. But for someone on the train moving past the scene, their motion vector is slanted, so from their perspective, the two strikes did not occur at the same time, because the light from each bolt reaches the observer at two different points along the time axis. Remember, from the viewpoint of someone standing still, the lightning bolts appeared to strike simultaneously. But from the perspective of someone on the train, more specifically, from their world line, it's the world that's moving toward them, and they are the ones who are stationary. But in this universe, nothing is truly stationary, everything is moving. Therefore, we always have slanted world lines, leading to different perspectives on the same event. At position A, the two lightning bolts strike at the same time. But at position B, lightning bolt 1 strikes before bolt 2, and at position C, bolt 2 strikes before bolt 1. From this, we can conclude, there is no such thing as simultaneous in the universe. That means, there is no universal clock. 1 hour on Earth is not the same as 1 hour on Mars and vice versa. So, time is relative, or more precisely, time is relative to the object in motion. Each moving object experiences its own frame of time, and the events that happen to it follow a unique sequence. Another object moving through the universe would perceive those same events happening in an entirely different order. Not only that, if we look closely at the vertical axis, meaning the time axis, we will see that the faster one moves, especially approaching the speed of light, the longer it takes for the second lightning bolt to reach the person on the train. This is precisely why we can conclude that, from the perspective of a moving object, the faster the speed, the slower time becomes. And when we reach the speed of light, time virtually ceases to exist because light is the fastest speed in the universe. The path of light on Minkowski's diagram can be considered the ultimate limit of all things. This means that everything moving slower than light lies within the light cone. Anything moving faster than light would lie outside the cone, but as we've discussed, nothing can travel faster than light. So, all movement that we can create will fall within that cone. But what if we draw a vector opposite this?